Let's solve problem number 3 on time complexity of loops. The topic of this presentation is time complexity of loops solved problem. Let's proceed and let's see the problem first. Here is the problem. Consider the following C code segment. This is the C code segment. Which of the following most closely approximates the return value of the function fun1? These are the options, and we need to determine which of these options closely approximates the return value of the function fun1. This is the function fun1, and this is the return value of this function. We need to determine the value of q. Let's now try to solve this problem together. For this, let's remove these statements and these options, and let's focus on this code. This is the code from the question, and now let's try to understand how this code works. Here we have function fun1 and we have this variable n. This function fun1 will receive some input, some value, and the value will be received in this variable. Within this function we have a total of 5 variables I, j, k, p and q, where q is initialized to 0. After this we have this for loop where I is initialized to 1, I is compared with n. If I is less than n, then the loop body will execute. After this, I will be incremented by 1. Clearly, this for loop will run n minus 1 times. Because the initial value of I is 1, after increment it becomes 2, then it becomes 3, then it becomes 4, and this will continue up to I equal to n minus 1, because this is the last value of I for which this condition is true. So for I equal to n minus 1, this condition is true. But for I equal to n, this condition is not true. So clearly, I has received values from 1 to n minus 1, and therefore the number of iterations of this for loop is n minus 1. Now within this for loop, we have this statement p equal to 0. This means 0 is assigned to p. Then we have these two inner for loops. These for loops are within this for loop, hence this entire structure is the nested loop structure. In this for loop, variable j is initialized to n. J is compared with 1. If j is greater than 1, then the loop body will execute, and then j is updated to j divided by 2. The value of p is equal to the number of iterations of this for loop. Why? Here we have plus plus p, which is equivalent to p equal to p plus 1. This means in each iteration of this for loop, p is updated to p plus 1. This means 1 is added to p every time when this loop runs. So in the first iteration, the value of p will be 1 because p is initialized to 0. After the iteration number 1, the value of p will be 1. After the iteration number 2, the value of p will be 2. After the iteration number 3, the value of p will be 3. And after the iteration number k, the value of p will be k. So if there are a total of k iterations of this for loop, then the value of p will be k. So it is clear that the final value of p after execution of this for loop is equal to the number of iterations of this for loop. We need to determine how many iterations are there for this for loop to know the value of p. And this value is important because the second for loop depends on p. Here we are using variable p. In this for loop, k is initialized to 1. K is compared with p. If k is less than p, then the loop body will execute, and then k is updated to k times 2. Here we are using variable p, so it is important to know how many times this for loop runs to know the value of p, which we can use here in this condition. Also, we can observe in this for loop, q is incremented by 1. Just like p, the value of q is same as the number of iterations of this for loop. So we need to know the number of iterations of this for loop in order to find the value of q. And we are interested in finding the value of q because this will be the return value of this function fun1. So eventually we need to know the number of iterations of these two for loops to find the value of q. After completion of this for loop, the value of q will be the final value which is returned by this function. So now we know how this code works. Let's dive into the solution. We first need to analyze each iteration of the first inner for loop. So let's take this for loop for j equal to n, j greater than 1, j equal to j divided by 2 plus p. We are focusing on the first inner for loop. Let's try to analyze each iteration of this for loop and let's find out the value of p. In the first iteration, the value of j is n. So j is equal to n in the first iteration. After this, j is compared with 1. Let's say n is greater than 1. The condition is satisfied. P is incremented by 1. And after this, j is updated to j divided by 2. So this time we need to divide j by 2. This becomes n by 2. So this is the new value of j in the second iteration. After this, j is again compared with 1. Let's say n by 2 is greater than 1. The condition is satisfied. The statement will execute and j is updated to j divided by 2. We now need to divide n by 2 by 2. We will get n by 2 square. So this is the new value of j in the third iteration. In the fourth iteration, the value of j will be n by 2 power 3 because we again need to divide j by 2. In the fourth iteration, the value of j will be n by 2 power 4. This will continue up to, let's say, n by 2 power k. As we can observe a pattern here, the first value of j is n by 2 power 0, which is equal to n. The second value of j is n by 2 power 1. The third value of j is n by 2 power 2. The fourth value is n by 2 power 3. Then it is n by 2 power 4. So clearly the difference of the powers of 2 in the denominator is 1. We have 0, then 1, then 2, then 3, then 4. Let's say the last value of j is n by 2 power k. This is the last value of j for which this condition is true. Let's assume n by 2 power k is equal to 2. Because for this value of j, this condition is true. And I'm assuming n by 2 power k is the last value of j for which this condition is true. If this is the last value of j, after the updation, it becomes 1. And 1 is not greater than 1. The condition becomes false. Hence, this is the last value of j for which this condition is true. So this is the reason why I've assumed n by 2 power k is equal to 2. Now let's try to solve this equation to find the value of k. Because if we find the value of k, then we will get the number of iterations of this for loop. Here we can observe a pattern. The power of 2 is 0 for the first value of j. The power of 2 is 1 in the second iteration. The power of 2 is 2 in the third iteration. The power of 2 is 3 in the fourth iteration. So one thing is clear, that the power of 2 depends on the iteration number. It is always 1 less than the iteration number. Clearly, for the last value of j, where the power of 2 is k, the iteration number must be k plus 1. As k plus 1 is the iteration number for the last value of j, it is equivalent to the number of iterations of this for loop. So there are a total of k plus 1 iterations of this for loop. Now we need to find the value of k in terms of n to determine how many iterations are there of this for loop in terms of n. Let's find this out. N by 2 power k is equal to 2. If we solve this equation, we will get k in terms of n. Let's remove this denominator by multiplying both sides by 2 power k. In the left hand side we will be left with n, and in the right hand side we will be left with 2 times 2 power k, which is equal to 2 power k plus 1. When bases are same, the powers add. So we will get n equal to 2 power k plus 1. Now we can bring this k plus 1 in the base so that we can find the value of k. For this we can take log on both sides. Let's take log base 2 on both sides. Why am I taking log base 2? Because log 2 base 2 is 1. We can eliminate this constant by using the log base 2. Hence I am applying log base 2 on both sides. And we know after applying the logarithm, we will get log n base 2 in the LHS and log 2 power k plus 1 base 2 in the RHS. Now let's switch LHS and RHS. We have this equation now, log 2 power k plus 1 base 2 equal to log n base 2. This equation is same as the previous equation. Now let's try to solve this equation. We know the property of logarithm. Log a power b base c is same as b times log a base c. So log 2 power k plus 1 base 2 is same as k plus 1 times log 2 base 2. What is log 2 base 2? Log 2 base 2 is 1. So we will get k plus 1 times 1, which is equal to k plus 1. So LHS is k plus 1. What about RHS? RHS is log n base 2. So the new equation is k plus 1 equal to log n base 2. Now we can subtract 1 from both sides to remove this 1, and we will be left with k in the LHS and log n base 2 minus 1 in the RHS. So k is equal to log n base 2 minus 1. This is the value of k in terms of n. K is log n base 2 minus 1, and we know this loop runs k plus 1 times. So if we replace k by log n base 2 minus 1, we will get log n base 2. And this means this loop runs log n base 2 times. And what about the value of p? We know the value of p is same as the number of iterations of this for loop. So clearly the value of p is also log n base 2. I hope this is clear. Now we know what's the value of p. Let's try to find the value of q by analyzing this for loop. So now our focus is on the second inner for loop, which is for k equal to 1, k less than p, k equal to k times 2, plus q. Now let's try to analyze this for loop. Before we do the analysis of this for loop, let's replace p by its actual value, which is log n base 2. Now we can analyze this for loop. We know in the first iteration the value of k is 1 because k is initialized to 1. After this, k is compared with log n base 2. This means 1 is compared with log n base 2. Can we say 1 is less than log n base 2? Let's assume 1 is less than log n base 2. So this condition is satisfied and hence this statement will execute. After execution of the statement, k is updated to k times 2. So the new value of k is 2 because if we multiply 1 by 2, we will get 2 as the result. So this is the value of k in the second iteration. Then in the third iteration, we know k is multiplied to 2 once again. So we will get 2 power 2 in the third iteration as the value of k. In the fourth iteration, we will get 2 power 3 because 2 power 2 is multiplied to 2. This will continue up to, let's say, 2 power t. I'm assuming this is the last value of k for which this condition is true. And I'm assuming t here in place of k because we are already using k in this for loop. To avoid any confusion, I'm using a different letter here. 2 power t is the last value of k for which this condition is true. Let's assume 2 power t is equal to log n base 2. I'm assuming log n base 2 to simplify the calculations, which we will do after this. Although I should assume lesser value than log n base 2 because the condition here is k less than log n base 2. So this value must be less than log n base 2, not log n base 2. And I'm not worrying about the constants because we are interested in the approximate value of q. So I can assume 2 power t is equal to log n base 2. Now let's find the value of t in terms of n. Why? Because in this pattern we can observe t helps us in determining the number of iterations of this for loop. Here we can observe the first value of k is 2 power 0. 2 power 0 is 1. So, in the first iteration, the power of 2 is 0. In the second iteration, the power of 2 is 1. In the third iteration, the power of 2 is 2. Clearly, the power of 2 is always 1 less than the iteration number. As the last value of k is 2 power t, the iteration number for this must be t plus 1. As this is the last value of k, so there are t plus 1 iterations of this for loop. Now if we find the value of t in terms of n, we will get the number of iterations of this for loop and eventually we will get the value of q. So now let's find the value of t. In order to find the value of t, we need to bring this t from the power to the base, and for this we can apply log on both sides. Logarithm helps us in bringing this power to the base. So let's apply log base 2 on both sides because here we have the constant 2. So now let's take log on both sides. After applying log on both sides, we will get log 2 power t base 2 equal to log n base 2 log base 2. We know the property of logarithm. Log a power b base c is same as b times log a base c. So we will get t times log 2 base 2 in the LHS, which is equal to t because log 2 base 2 is 1. And in the RHS we have log n base 2 log base 2. So t is equal to log n base 2 log base 2. We know the number of iterations of this for loop is t plus 1. If we replace t by log n base 2 log base 2, we will get log n base 2 log base 2 plus 1 as the number of iterations of this for loop. And as we know the value of q is same as the number of iterations of this for loop, so the value of q is log n base 2 log base 2 plus 1. But we want the approximate value of q, so we can eliminate the bases and the constant. We will get log n as the result, and this is the approximate value of q. So q is equal to log n after completion of this for loop. But remember, this is not the final value of q. We will get this value after completion of the first iteration of this for loop. For I equal to 1, this loop body will execute, and after execution of this loop body, we will get log n as the value of q. Then in the second iteration, the value of I will be 2. This loop body will again execute, and log n will be added to the previous value of q, and it will make it 2 times log n. So in the second iteration of this for loop, we will get q equal to 2 times log n. In the third iteration, we will get 3 times log n as the value of q. In the fourth iteration, we will get 4 times log n as the value of q. So if we are assuming there are a total of n iterations of this for loop, then we will get n times log n as the final value of q. I'm assuming the nth iteration is the last iteration of this for loop. In place of assuming n-1, I'm assuming n here for the sake of simplification. And as we are interested in the approximate value, we do not have to worry about the constants. So I'm assuming there are n iterations of this for loop. And if there are n iterations, the final value of q will be n times log n. And this means after completion of this for loop, the value of q will be n times log n. And hence, the return value of this function must be n times log n. Therefore, the close approximation of the return value of fun1 is n times log n. And hence, option D is the correct option. So this is the close approximation of the return value of this function fun1. I hope this problem is completely clear. So with this, we are done with this topic, and this means we are done with this presentation. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.